apologize for this, but we're going to do one last video just to get all the topics done since I won't be there and I want to keep you guys on track with the other class. So we left off the other day where I introduced to you the Snell's law equation. So this is the refraction equation. N1 sine theta 1 equals N2 sine theta 2. I mentioned before that what you're going to end up doing is putting the indexes of fraction and the angle that it's in that medium in together on one side of the equation, and then you do it for the other substance N2 and theta 2. The one thing that you just need to be careful of is the angle. The angle must be taken to the dotted normal line. The big thing that they end up doing, like the only way that they can make this question tougher, is two factors. First is sometimes they'll give you multiple angles, so they'll give you this angle, this angle, this angle, and this angle. So they'll give you four angles, and you have to pick the correct one. Again, whichever angle's next to a dotted line, that's going to be what's going in there. You do also have to make sure that the angle and the sub and the index kind of go together. So whatever angle this is in air, then the index should be for air. The other way that they make this question difficult is sometimes they'll give you a protractor and ask you to measure an angle. So you want to make sure that you know how the protractor works, right? You line up the dot to where the cross section of the normal line and the boundary is, and you line up the edge of the protractor with the normal line, and then just record the angle that's less than 90. Those are the three steps. So the dot goes where this cross section is, it lines up with the normal, and then you read the angle either to this one or to that one, whatever. That's pretty much it. So here's the first question. Pause the video, work itself, and we'll go in a second. All right, so we're going to do the Snell's law equation. We have crown glass and diamond, and in the crown glass we have 30 degrees. So you go to the reference table, we write N1 sine theta 1 equals N2 sine theta 2. We plug in the index of refraction for crown glass and the 30 degrees. Because the 30 degrees is next to this dotted line, we're going to use it. One thing to keep in mind is I have to make sure that the crown glass and the 30 degrees are together. Doesn't matter if it's left or right side, as long as they're together, that's all that matters. Then I put the 2.42 for diamond, solve for theta 2, and we should end up getting 18.3 degrees. Now, the other day I talked about how the material that has the higher index of refraction should have a smaller angle. And what we can do is we can use that as a way of judging to make sure that we are on the right track. So because diamond has the highest index of refraction, it should have by far the lowest angle inside of it, which is what we get. So it's just a way of checking. Again, you don't need to do that. All right, here's the next question. Pause the video, work itself, and we'll go over in a second. Okay, so what we're going to end up doing is, again, Snell's law. So we do N1 sine theta 1 equals N2 sine theta 2. We plug in our numbers. Now, you do kind of have to be careful of what angle and what material it's traveling in. So it's saying that it's traveling in air, and then it's incident at 30 degrees. So air and 30 degrees go together. So 1 and 30 degrees, and the unknown medium is 12 degrees. So x and 12 degrees. So we solve and we get 240, and based off of our the reference table, this could be diamond, all right? Because 2.42, it's the only one that's close to it. All right. Here's the next one. Pause the video, work itself, and go for a second. All right. So we'll start off. We do again the Snell's law equation. We plug our number in, and then we get the theta 2 equals 72.2 degrees. Easy enough. Now, it does want you to draw the diagram. Now, I do recommend that you try using your protractor at least once at this point. But you take the protractor, you line it up like this. 72 degrees is right here. Again, you might see larger angles. We don't care about those larger angles. We find 72 degrees, and we draw a line like that. Easy enough, right? Okay, so that's pretty much it for refraction. Now, it is important to kind of be aware of what happens if two mediums are next to each other and have equal indices. Now, if you recall, I made a comment that as far as waves are concerned, boundaries only exist when there's a change in speed. Because light traveling, because objects that have equal index of fractions means that light will end up traveling at the same speed. If you have two materials that are next to each other, side by side, and light passes through them, if they have the same index of refraction, light is not going to notice that they are different materials. For the most part, if we put glass inside of water or we put ice inside of water, we can actually see the outline of the shapes. We can see the water and the ice as two separate objects. We can see the glass and the water as two separate objects. And that's because of the fact that the ice, the water, and the glass all have different indexes of refraction. Even though they're all clear to us, and realistically, clear plus clear should still be clear, we can tell the difference because light's going to start bending differently as it passes through the water, through the ice, and then back into water before it reaches our eyes. However, something cool ends up happening if we end up having two things that have the same index. Essentially, light acts as if there's nothing there. So here we have a test tube being put into water. Again, we can clearly see the test tube because the test tube is filled right now with air. It has a different index of fraction of water. So we end up having three different mediums that light is traveling in. And after it gets poured in, it fills up with water. Uh, it sort of disappears because now, the glass, while different than water, is still fairly close, but we can still see that that is something there, right? We could see the outline of the glass. Now the person's going to take some glycerol, a special glass, and pour it into the cornel. Again, at first, it looks like we can tell the difference, but once he fills it up with the corn oil, all of a sudden it disappears. The glycerol and the corn oil have the same exact index of refraction. So as far as light is concerned, they're the same medium. So light does not change the way it passes through, which means we cannot tell that that is something else. And they do end up going really close. And for the most part, it is pretty much impossible to see. You might be able to see some of the air bubbles, lining the edge, but besides that, you cannot find where the glycerol test tube ends and where the corn oil begins. Now, before anyone asks, know if you try to you can't make a invisibility cloak by getting clothes that have the same index of refraction as air because it won't make you invisible, it'll make your clothes invisible. All right. Now, two more things that we have to talk about. Again, keep in mind that these are things that you just have to be able to recognize. One of them is polarization. All right. So, polarization, first and foremost, is that it only affects transverse waves and, in particular, light, because light is a double transverse wave. Remember, transverse means that it has has the crests and troughs, ups and downs, looks like a sine curve. So polarization only affects those types of waves, and in particular light, because light is, as we call, a double transverse wave. It has a vertical component to its ups and downs and a horizontal component to its ups and downs. Now, what is polarization? The main idea of polarization is that it's a filter. Only one of the directions ends up canceling out. So the light will come in through a polarizer, and that polarizer will filter out one of those two components. So if we send it through a vertical polarizer, it basically filters out the vertical part of the light wave. So it cancels out the horizontal and only allows for the vertical. If you send it through a horizontal polarizer, it'll only allow the horizontal part to come through and it filters out the vertical. And of course, if you have a vertical and horizontal next to each other, it cancels light out completely. Basically, this is the kind of diagram that you see. You'll see light coming in. It has a vertical and horizontal. It goes through something, some line, some film, and then you'll only see a vertical part. And then they'll ask you, "What is this?" And you just have to recognize, "Oh, this is a polarizer." That's it. The reason why we use it, some people might have them in their glasses that have polarized lenses, or if you are taking one of the photography classes, you might know about polarized camera lenses. The idea is it gets rid of glare. The reason being, and this is just a side note, you don't need to know this, but when light bounces off of surfaces and produces that glare effect, what ends up happening is the horizontal component of light ends up being bigger than the vertical component, and that's what actually produces this glare effect. So what the lenses will do is they'll cut out that horizontal component, cut out the horizontal to get rid of the glare, and then you only see the image. And that's why you still see things, but it's kind of darker, but it also looks clear. Like I said, if you have polarized lenses, you'll know exactly what I mean. I could show this in class on Wednesday because I have two polarized lenses. All right, here's the first question. Pause video, work stuff, and we'll go over in a second. All right, the answer is no. Sound is a longitudinal wave. Polarization only affects transverse waves, so no, sound cannot be polarized. Here's the next one. Pause video, work stuff, and we'll go in a second. All right, so this is what I mean when I said like you just have to be able to recognize the diagram that shows polarization. We have a vertical beam, a horizontal beam. It even says vertical and horizontal plane, and then all of a sudden we only get one of them. The idea is it's a filter, polarizer. So boom, this box is a polarizer or a filter. I think that's the best way to keep in mind what polarizer is. Just write filter, and there you go. It will make a whole lot more sense. All right, this is the very last topic, and again, for the most part, you just have to be able to recognize this. Now, there are going to be some questions dealing with numbers, but there's no calculations, and you'll see what I mean in a second. All right, Doppler effect is the term we use for an apparent change in the frequency of a wave. I mentioned before that the frequency of a wave is an inherent trait to the wave itself, meaning that as the wave travels from one medium to another, it doesn't matter how its speed changes, doesn't matter what's going on, doesn't matter if it's losing energy or gaining energy, its frequency always stays the same. The frequency never changes. Again, it's an inherent trait to the wave. However, the Doppler effect is the only time where the frequency, quote unquote, seems to change from our perspective. And the reason that this is caused is because of the motion between the wave and the observer. So whoever is sending out the wave and the person listening to the wave, there's some sort of motion between them, and that's changing how the frequency is perceived. Um, it can The frequency can go up, it can go down, all depending on how you move. And this is particular, like the main example that you tend to see this with is fire trucks or ambulances or any sort of car that's traveling past you. You might notice that they sound higher pitched as they come towards you, and then they kind of their pitch drops the moment they pass by. That's the Doppler effect. All right. Now, if you're motionless, there's no change. The sound kind of goes outwards, and the wavelength is the same all around. All right, so nothing crazy. But once you start moving, what you'll notice is that the waves that in the direction that the object is moving towards will start to get bunched up. So if you have a car and it's releasing sound waves, the next time it releases that next pulse, essentially, it's moved forward. So the waves kind of get bunched up in front of it, and then the waves also get start to lag behind it. So the wavelength decreases over here and increases over here. So what we end up getting is a higher frequency as it moves towards us and a lower frequency as it moves away from us. For sound, this just means that it sounds higher pitch coming towards us and lower pitch as it moves away. But when it comes to light, which we'll talk about in a second, just means that it'll end up getting shifted to be more bluer when it's coming towards us, or shifted more to the red as it's moving away. Again, that's pretty much it for Doppler effect. You just need to know that as it moves closer, the frequency increases. As it moves away, the frequency decreases. Um, that's pretty much it. Though there are two other things to keep in mind. Like for example, if you end up moving at the same speed of the wave, what ends up happening is you just won't hear it or see it until the moment it passes you, because the waves don't have time to actually move ahead of you. Like every time, like you're almost moving along with the wave that you're producing. So there's no sound, and then all of a sudden the sound as they pass by. But something ends up happening once you end up going supersonic, once you go beyond the speed of the wave that you're producing. Now, for the most part, this is most common with sound waves, since the speed of sound is only 343. But once you travel faster than that, you end up creating this sonic boom effect where the waves kind of overlap on each other, and you can get this massive pulse of energy that could be strong enough to shockwave to break glass and set off alarms and all this stuff. There's a lot of really cool things about this. Now, you can find pictures of things breaking the sound barrier and producing these sonic cones and stuff. Pretty cool stuff. One thing that's interesting is to ask yourself, well, if we can make a sonic boom for sound, is it possible to do this for light? Well, the first response would be no, because as we know, there is a hard rule in physics, which is nothing can travel faster than the speed of light in a vacuum. So it is impossible for anything that, especially if it has mass, to get to and exceed the speed of light while traveling in a vacuum, in the vacuum of space. However, that there's no rule about breaking the light barrier, going faster than the speed of light in any other material. As we've learned, light travels slower in water and diamond and in all these other materials. So technically, it is possible to break the sound barrier, the light barrier. Sorry. There's this really cool phenomena called Cherenkov radiation. It basically only occurs during nuclear reactors. That's the only time this happens. But what ends up happening is the electrons will end up traveling at near light speed. And during that time, because the reactors are submerged in water, you end up having light traveling at a much slower speed, about one third of its usual speed. And the electrons will be traveling faster, and it gives us this really cool, eerie blue glow. All right, so there is a light sonic boom. Now, Doppler effect is extremely important for astronomy. It's how we know what stars and galaxies are moving towards and away from us. It's how we know that the galaxy is expanding, and it allows us to know pretty much everything. Basically, as you should have learned in chemistry, every element has a fingerprint essentially from when you look at it through a spectroscope. Very specific lines of color, of frequencies of light that they give off or absorb. And we can use that to identify what type of elements are out there. Since most things are composed of hydrogen, what we can do is we can look at a galaxy, know exactly what the hydrogen lines should be, and if those hydrogen lines are shifted over to the red, that tells us the galaxy is moving away. And if it's shifted over to the blue, we could tell that it's moving towards us. Also, this is not something we're going to do, but depending on how much it's shifted, we could actually figure out how fast it's going. So not only could we figure out how that this galaxy A is moving away from us, but we can figure out exactly what the speed is based off of how much is shifted. As far as we're concerned, though, we just want to know whether the frequency would be higher or lower. That's it. We do not need to know about specific speeds or anything like that. All right. So use that at your to your advantage. Yeah, so again, it's pretty much the same thing. If you're moving closer together, your frequency increases or it becomes blue shifted. Or if they're moving farther apart, the frequency decreases and they're getting red shifted. There's a bunch of phrases that you can use. These were all phrases given to me by students. It's all the same thing, that away is red and towards is blue. Whatever helps you. Okay, here's the first question. Pause the video, work itself, and we'll go in a second. All right. So as the car approaches a pedestrian, it's giving off its horn. Because they're moving towards each other, we know that the frequency is going to be higher. We know the pitch is frequency, so that's also higher. And we know that the wavelength is going to be smaller. It's going to be more bunched up. All right. Here's the last one. Pause the video itself, and we'll go over in a second. All right. Now, this is what I meant before when I said that we don't have a way of figuring out how much the frequency changes and how that relates to speed. All we know is that it would either go up or go down. So I know for a fact that since A and B are both less than 350, neither of them could be the answer, because if the frequency did decrease, I would not be able to tell if it was supposed to decrease by 20 hertz or 30 hertz. So neither of them can be correct. Because the car is moving towards an observer, it has to have an increased frequency. So the answer is D. And that's it. If you have any questions, please let me know. Otherwise, good luck and have a great day.